Okay, please start. You started, yeah. Okay, excellent. In my previous lecture, we actually considered the case of the local asymptotics. And so they are, and this is the reason that this asymptotic is not so accurate, because it's not taking the, in mind, global picture. And so, of course, it's different from the full numerical solution to very sufficient value. And in order to accommodate all this stuff, about 20, this local asymptotic approximation was invented by Busset. And after that, about 30 years passed, or 20 with something, I don't remember. But, and only then in 2002 and 2000, it was sort of the end of the story, because when the global asymptotic solution was found. So let's start this chapter. This chapter is 5.3. It's about, as I already told, global asymptotic and in a sphere. Here. And actually it's based on the paper of Jones, on the papers of Jones, Soward, and other authors. As I already told you, it was started in 2000. It is important to appreciate that the theory outlined above in my previous lecture is strictly local, both in space and time. So it's both in both space. From the initial value point of view, the description is valid for a limited period of time, but does not necessarily determine the long time evolution of small disturbances. Linked is that this statement was made by Soward 97. And link is the fact that with the time dependence separated out, the local spatial structure cannot necessarily be extended throughout the spatial domain and still meet the boundary conditions. This statement was made later by the Gian. Sorry. Anna. Gian in 1992. It was proven, actually. It is important to understand that the local in space theory does not necessarily provide an approximation to the complete, or we name it like a global eigenvalue problem. In fact, for our convection problem, the local results do not even provide approximate of the true global solution in the limit of E going to 0. let's just stress that it's not. The local and global result differ by an order of magnitude amount. It's very sufficient. And it, as explained again by Soward and Gian, that provide all the explanation for that. Again by Soward and Gian, this means that previous local solutions do not provide approximate edging solution of the problem they probe to solve. Also, the actual radial dependence of the marginal mode is not included in their analysis. An attempt to define the radial dependence of marginal convection in this asymptotic limit is what made, first of all, it was made by Soward. So let's stress it once more. It turns out that within the framework of the previous asymptotic treatment, it is not possible to define the radial structure of the convection in a consistent manner. The result implies that Roberts and Bousset's analysis does not affect a correct critical Rayleigh number of the system at leading order, even at leading order. And again, we return to this famous paper of John Soward and Moussa, 2000. And so Jones and Soward and Ali Moussa in 2000 offered a correct critical number of the spherical self-gravitating system by resolving this difficulty and hence define the radial structure of the critical mode in consistent manner. So actually in this Jones, Soward and Moussa, let's stress it again. So it was very good paper, which actually did everything necessary, and Moussa, it was made in 2000. So it's very important paper. So actually in this paper, consider the case when the full sphere is filled with Bessonnesque fluid and there is constant heating stuff which heat everywhere, and the heating is distributed uniformly. Actually, Jones et al. Considered the case of stress-free boundary condition, nothing that in the limit of small Ekman number. There is no leading order distribution, distinction of between rigid boundary and stress-free boundary, as the Ekman layer make only higher order correction to the critical Rayleigh number. So actually why they considered stress-free condition, actually it's applied to any condition, boundary condition, and no slip as well. So actually they provide this scaling, and maybe the most important thing in this scaling, that if you remember the local approximation, you hear, instead of the integral over the some wave number, you had in the local asymptotic approximation, you had just number. So it will be wave number. But here there is not wave number, there is some sort of the packet which depend on the cylindrical radius S. And of course there is a structure which gives the temperature dependence, like e to the 2/3, and this gives a special structure like E1 over 1/3 in power 1/3, 1/3. So it's resume the Stevensson layer, maybe you see. But the main ingredient for the globality is this one. it's very sufficiently different from that. Okay, our primary objective is to construct a valid WKBG solution of equation 510 and up to equation 512, which I listed in the previous lecture. And of course, they remain the same. And with this satisfies of all appropriate boundary conditions in that form, which I already stressed it out. And we are guided by the result of asymptotic theory above. It is anticipated that omega and k both vary on the length scale of OD1. So omega and k are both varying on the scale of OD1. In the sphere. In addition, for given m, r, and omega, r is also very important because it's and omega, the function k from k at s is determined by the dispersion relation, which was local now, but now we will turn out to the proper dispersion relation, while the function omega, all the function, is uniquely defined by the corresponding solution of the equation which is stated before as at the numbers 515 and 516, and up to an arbitrary multiplicative function of s. So you see that here there is also one more important ingredient, because we not only have this function which changes fast, but there is a function W, and of course we are looking for other function in the same similar manner, and it depends in order one depends on the coordinate in the axis of rotation, in the direction of the axis of rotation, and on this value, which is actually the cylindrical radius. So there is also very sufficient addition in comparison with the local asymptotic analysis here. So since k only appears in the dispersion relation for omega in the combination actually k square, so if we put it in the equation, so then this stuff appear only like k square. The local condition is satisfied simply when k is equal naught. So the local k is equal naught. And then both the real and imaginary part of the omega and dk are vanished. So actually, the omega dk, all the part, imaginary and real part, actually zero. The point SL, there is some special point SL. We mark it with L, at which the omega dk is equal naught. This one thing. Okay, maybe I put it better here. Exactly at this point, we have SL. Here small l and the index L. So at this point, the omega per dk is equal naught correspond to the double root of the dispersion relation, where two distinct WKBG solution, actually Ks and minus Ks, they are somewhat split on this. So there is minus Ks and Ks. Okay, and they actually have to coincide. The certain issue of the eigenvalue problem is to connect those two WKBG modes, these WKBG modes, which decay exponentially to zero on both sides of this cylinder and this cylinder. There is some special cylinder, which is actually the cylinder around which we have this nice cartridge bell structure. The connection problem outlined above is resolved locally in the neighboring of the SL by considering the amplitude equation given by Gian. And this is equation in our notation is 5.3, which is similar to actually the above equation 5.25a. So actually this follow it from the formula 5.25.8 from the previous lecture. And so this is actually this finding was first made by Gian. Okay, 1992. Let's put that way. Okay. So the only significant difference is that the term proportional to this distance in squared, because we're working on the both side. So the term proportional to S minus SL in square is neglected in comparison with the large term proportional to S minus L. So actually we neglect by that in favor of S minus SL. Maybe more precisely to say model. So Gian terms linear in S and SL. Of course, this is the sort of the linear dependence. And so is neglected in comparison with the larger term. And Gian's terms linear to this value is present because there is no zero phase mixing. Okay. It's not written here. Okay, this is the summary of what I just told to you. You just maybe better understand it just reading it out. And then for this linear term, this relation are present because of there is no non-zero phase mixing actually. So at this cylinder, this special cylinder which is at S equal SL, we should satisfy non-zero phase mixing, which is, I didn't found it here. Okay, let's put it another way. This is zero phase mixing is that real part of d omega by ds on this cylinder. L means that this is special cylinder, which was found by Gian, and it should be such a condition should be satisfied, that it's not equal not. As Gian pointed out, the resulting I equation has no solution that decay to zero on both sides of SL. By implication, it is impossible to connect the two appropriate WKBG, these two appropriate WKBG solution across this cylinder, at least SL. Indeed, there is no value of the Prandtl number at which this condition is satisfied. The point is simply that the R slightly above the RL, whereas the R is modified Rayleigh number. So we have the sort of the critical Rayleigh number and the modified Rayleigh number, which is scaled out from the Ekman number I showed you in my previous plot. This Rayleigh number is just slightly, let's tune it this way, just slightly greater than this marked right RL, which is means that it's near the cylinder. The point is simply that with this R slightly above RL, phase mixing shortens the radial length of any initial disturbances, causing it to ultimately decay. And to find a satisfactory solution, okay, this is just repetition what I already told. And this is, let's jump to this point. To find a satisfactory solution, we must follow Soward and Jones, 1983. It's okay, it's written here. We should follow Soward and Jones, 1983. And consider the analytic extension of the exact solution separatable in azimuthal phi and time t. So we look for this solution of this time. It's quite similar to the solution we form, which we also used on our previous lecture. So of the entire convection problem into the complex S plane, actually, this synthesis working. For real S, where S is the radius of the cylinder, that solution has the asymptotic WKBG representation. Clearly, it also provides the asymptotic WKBG representation of the analytic extension, provided that W, small w solves corresponding equation, albeit for now complex S. Okay, this is also important point, that we should go to the complex space to resolve this problem. Tackling partial differential equation with two essential variables here, S and Z, so we keep this dependence of S and Z for the one. By technique whose origin lies with one-dimensional problem was the main thrust of the Soward and Jones development, this Soward and Jones 1983. Okay, and once this point is appreciated, the key step is to determine the corresponding analytic extension of the dispersion relation, which we state in our previous lecture. But now we should rearrange it by the recipe, describe it, by this recipe which will be following, describe it. Except for this added complication, this complication is that omega is the eigenvalue of ordinary differential equation rather than solution of algebraic equation. So this is perhaps the main essence of the global application, that the omega, let me repeat, is the eigenvalue It's any eigenvalue of ordinary differential equation, and not just consequences of some algebraic relation. So this may be very essence of the global approximation. Omega is. Okay, and up to this extent, our analysis parallels to Janus' development in 1992. To begin, we locate a point S equal SC. Is it written here? Yeah, exactly. Look how it's written here. This index C, where we set to zero derivatives of the this integral wave number and the corresponding cylindrical dependence. In general, so to begin, we locate this cylinder at S equal Sk. So we locate for this picture S equal Sk. Okay. So the and wave number k equal k, we locate both of them. Okay, let's put here. At which both the complex group velocity and complex phase mixing vanishes. So it is important to mention that all these relations are complex. So complex group velocity and complex phase mixing. Phase mixing meaning time, and this. Oh, sorry. This group velocity means, of course, in space and in direction of cylindrical radius, because chi is actually working in direction of cylindrical radius. In general, this means that both S, K, and KK, these both values, are complex. So this is actually a complex relation. And it's regarding to the eigenvalue of corresponding second order boundary condition equation. So they both are complex. For our problem, however, though the location SC is complex, the wave number is real and simply vanishes. So we just use this simple relation for wave number, that it just simply vanishes. And just as it does in the case of the local analysis. Here there is coincide with the local analysis. And our extra-relic mind, actually the main difference is here, that the phase mixing vanishes enables the convection problem which occur when the wave number has a repeated root to be resolved. It is accomplished by the considering the local modulated representation. And this local modulated representation look like that. You see that here we have some local representation, and it's actually appears to be that it's working in this scaling. Okay. And it's important to stress this out, that actually inside this cylinder, in cylindrical direction, we have quite another dependence, like a square of this e to the 1/3. So it appears to be e to the 1/6. This is actually the thickness of this distance, which is again in some way similar to the Severson layer, but it's quite another nature because it's convection one. And this condition is valid in the neighborhood of Sk. A match is obtained with the WKBG solution, provided that actually we base on the corresponding WKBG solution that we satisfy this condition and in this limit. And since our key C is equal not, and it's actually repeated root. Is a repeated root of the dispersion relation which we show in the previous lecture. There is a second neighboring root. Okay, hopefully I have it. There is a second neighboring root which is satisfied to this condition, as it's written here. I'm just repeating, for which this condition is satisfied. And our limiting processes points to the fact that dk by ds, the direct derivative of the k from the s, which actually enter to the integral, is not uniquely defined at s equal sc, and highlights the importance of the matching condition. So actually we match these two roots of the WKBG mod, and so we expect this uniqueness. Eventually we have unique solution. And notice that the radial length in the vicinity of this cylinder s equal sc, this one, this is for the Ekman to the 1/6. Let's just remind this. So this here we have for the e to the 1/6. And I showed it in the previous slide. This dependence. Okay. So notice that there is such a relation, and since our k is equal not at this position of the cylinder, so only the phi derivatives influence the lowest order results. Only the full influence first order results. And at say at about or for the 1. At so okay. Okay. So in this domain we can work like that. And it is actually our ordinary differential equation, which we show how to solve under the certain boundary conditions. And it's not eigenvalue, not the characteristic equation, but exactly the equation of ordinary differential equation of the second order, whereas the x is actually the correspondingly modified distance inside this cylindrical radius. Let's just repeat it. So we start to begin to capture the influence of the radial s derivatives, but the z derivatives remain small. And it is at this level we obtain the amplitude equation. So actually we obtain the amplitude equation, which is the main equation in this sense, and it's work with the limit that y tends to naught as x to tend to infinity. X means that it's exactly the relation which is in this, which is applied in this form. And it's important that also there is some representation of the Rayleigh number in powers of e to 1/3. And again, in power to the e to the 1/3, there is representation of azimuthal stuff, and the same is dependence for the omega value, which constitute the time dependence. So the simple representation, this simple representation, which is on the bottom, all these three things, stems directly from the small k expansion of the dissipation relation, which was in the previous lecture, using the asymptotic result. This asymptotic result which we used is written here, and there is also some repetition how we got it, and which follows from the functional dependence of small w dependent on s and z in the previous formula for this wave number dependent on the cylindrical radius. And the consistency of the two representation, 5 to 2 and 5 to 4, this two representation. And by this device captures all the appropriate terms of order e to the 1/3. Interestingly, at the higher level, which is actually e to the 1/3, 1/6, sorry, e to the 1/6 at this higher level, we might have expected larger terms of the derivatives of this dy by dx. And actually this product of x over y to appear in this previous formula which I show you, 225, this one. And so, but these terms, actually it's linear in k and x, are absent because of our ansatz 5 to 3, this ansatz, this one, 5 to 3. And this also which works here. In their absence, the structure of the amplitude equation is controlled by the second partial derivatives of omega with respect to both k and s, which are the coefficient of the quadratic terms in the dispersion relation expansion. Significantly, in addition to the Laplacian scaling, actually this scaling is come from the Laplacian because it's second order derivatives. Already mentioned it, and they by ds and s compute to the level of approximation taken, and this leads to the absence of the term, actually the term of x dy by dx actually absent. That simplify a lot. Which is linked to the result that result oh, sorry. Okay, it's not written here, but in fact, we have that this value, which differentiated on both value, it's in some point that it's vanished, and this is equal 0. Let's just write it down here, that the 2 omega by dk and ds again at this complex cylinder is vanishing. So we are almost in a semifinal, which remains, oh no, it's a sufficient part remains, sorry. Okay. And the consequences of omega being a function of k square and k, and actually this is inconsistent that omega is a function of chi squared. And so we could work at chi s equal naught in this condition when they're taking the derivative. Finally, we emphasize that the only way to that derivative influence the problem is through their connection with the Coriolis acceleration and the processes encapsulated by the equation from the previous section, which is the equation 515 for this small w. Okay. The location at which the coefficient of Y in 3.25 vanishes are called tuning points, and this is a famous tuning points at which we should match everything. comparison with the numeric to define. Actually, to compare with the numerical stuff, it's quite useful to define this value. And where in this representation m with the index capital N is actually the value of m predicted by the numerical solution. So this is just numerical. And actually we have the correction which is due to the analytical solution. And it should be emphasized that though this choice influences the realized frequency correction omega, the realized value of R remains uniquely defined by the imaginary part of the formula which is from our previous section. Okay, it seems that we finished this chapter. It was mainly theoretical in some sense, but nevertheless it provides us with the, I just try to draw how this picture works. Maybe the most important essence of all this analysis is that we have identified one cylinder. You can call it stellar cylinder. Of course, the cartridge belt structure appears here, and the important message that the thickness of this cylinder is e to the 1/3, but if we consider e to the 1/3 is actually in the azimuthal direction. But if we consider the cylindrical direction, okay, let's just stress it, that e to the 1/3 is in azimuthal direction. And here we have the cylindrical direction as, okay, let's have this addition in order to understand how it works. And it's work in the cylindrical direction, like e to the 1/6. And it's this actually, scaling actually successfully provides us this global solution. So, okay, it seems I finished this chapter. So maybe there is a question. Questions? In this short, of course, there are many words about this stuff because it's rather complicated stuff. But eventually, it's operates just with the second order equation, and we describe everything with it, just to investigate different parameters. And the very big difference, very essential difference between the asymptotic analysis and this global analysis. Oh, sorry. Is actually that we using this and that. And the main feature is here that we still have e to the 1/3 dependence for the azimuthal case. But here the dependence is not clear. And we just realize that actually it is e to the 1/6 after this careful analysis of this integral. And this is the, and then we have two different solutions on both sides, and we just merge them, that they satisfy all the conditions around all the sphere. And so it's work it out that here we're getting eventually more wider direction in this direction, and in the direction of the axis of rotation, we have still keep the same e to the 1/3, and this is perhaps the crucial thing which is necessary to take carefully. But eventually the obtained asymptotic values becomes very close to the numerical values. One example is shown here. So it was made the full numerical research for this case, and it's very well coincide with the asymptotic estimation. And actually, of course, we can, on this approximation, we cannot better coincide of the uh, numerical and asymptotical solution, but we are restricted if we consider the first order of the solution, then we are working with the accuracy about e to the 1/3. It's rather good accuracy because even in the worst case, when we consider, in the worst case, when we consider only Ekman number of the turbulent nature, even in this case, we have the accuracy e to the 1/3 about 10 to minus 3. So it's still very good accuracy. But of course, we can go to the further, higher approximation, and then we have much more better accuracy. And it's very well coincide with the direct numerical calculation. So this is sort of the other big advance that actually we solve so complicated problem. We and reduce it to the just ordinary differential equation, but of course with very many parameters, which is necessary too much and to discuss and so on. But nevertheless, the result is quite impressive from my point of view. Okay, is there any questions? A break? Okay, let's have a break, and then we'll finish. turbulent point of view, anyhow, it's very small, and we operate with actually effectively, as we show you in the previous lecture. Of course, the picture remains the same of e to the 1/3 values, so e to the 1/3 we can calculate. Then maybe now we make some link to the magnetic field of the terrestrial planet from the this convectional stuff. And if we see the magnetic field of the terrestrial planet, you see that the Mercury has some own magnetic field. Venus has no magnetic field. Earth has its own magnetic field. Mars also have no like a Venus magnetic field. And we can say that perhaps the reason is the convection, because maybe convection in Venus and Mars is not powerful enough just to excite the dynamo. And how it's powerful, we can, of course, estimate from this asymptotic estimation. And we are working in such a system, which is shown here. And this is actually start from the original picture, which made by Bousset. You see that, again, we have this in a core. There is a heat flux, which is coming out, and we denote it as a QY. And there is a heat flux, which is going outside the outer boundary and going outside the inner boundary. In case of the Earth, we can consider that this heat flux, which comes from the inner boundary, is usually greater than adiabatic heat flux. And even with this heat flux, we can imitate somehow the condition which exists for the compositional convection. So this heat flux, at least in the case of the Earth, is always working. And there is, I lose my, this mouse, okay. And there is the output heat flux on the outer boundary, which boundary between the fluid outer core and mantle. And this heat flux could be greater than adiabatic value, or there are some researches that indicate from the seismic research that it's maybe perhaps lower than the flux from the outer boundary. And so eventually we could have sort of the stratified structure here and non-stratified with the sufficient buoyancy instability here, and the situation is evolved, and we have the very strong convection in case of the Earth, and perhaps due to the slow rotation of Venus, we have no similar convection in the Venus, because the only main difference between Earth and Venus is actually their angular rotation, because actually the Venus rotates almost 200 times slowly than the Earth, more precisely 200 times 50, something like that. So perhaps it's the main reason why the Venus has not so strong convection, and it cannot break the condition for the existence of the own magnetic field. And also we should take into consideration that the outer boundary of the Venus is very hot. So there is no such a condition that the heat flux going out properly from the Venus, and so maybe it's another reason for the convection. If you want to discuss the Mercury, just to finish this picture, whereas there is no magnetic field now, but there is a remains of the magnetic field, which indicates that in the past, in the deep past, on the Mercury, on the Mars, it was valuable magnetic field, and it was water, everything was wonderful. But eventually the condition is that this Mars is, radius of the Mars is approximately almost 2 times less than the Earth. So if the Earth, for cooling down of the Earth, it requires maybe some billion years. There is an estimate, of course, when the Earth completely will be cooled down, not completely, but sufficiently. So this actually depends on the square of the size. So if we very roughly consider the it appears the picture that from the estimation for the Earth core, we have the time just maybe 2-3 billion years more. We have maybe 4. It's, of course, it's not exact approximation, but in a period of few billions years, the Earth is cooling down, will be cooling down up to the state where there is no convection at all. But for the Mars, this time is should be divided by the ratio of the radius of Earth to Mars and put in square. So you see that for the Mars we just have something like 1 billion years, maybe even less than 1 billion years, just to evolve from the developed convection to absence of any sufficient convection. So maybe in just a few words, this is the reason. But our goal is to find the critical condition for existence of the convection, and at some critical convection even didn't exist. And we, of course, start from the same equation which we discussed with you before. I will not repeat them, they just listed here. So, and then we also has the approximation that there is an assumption in the Busemesk approximation, and actually the work which was done is was done actually by the approximation that the divergence-free condition, but not complete divergence-free condition. There is some deviation of the density, but there is a condition that the full density, full adiabatic density, is much greater than deviation of the density. And this deviation of the density actually produces Boussinesq type adiabatic flow. And also we operate with the temperature equation. In this temperature equation, we consider the contribution to the heat transfer due to the temperature and due to the pressure. And the temperature contribution is much greater than the pressure contribution. So in some extent, modeling via the entropy, as I already told, we can still have this contribution valuable from the entropy and not valuable from the pressure. And we can neglect them. So finally, we arrived at these estimations where we can estimate average density, density variation, and this T heat and P heat, and T buoyancy and P buoyancy. And so everything is matched quite well to the picture which I just showed you. Here we also include the Jupiter and Saturn. And the Jupiter and Saturn situation is quite favorable for developing the convection. The same, the slightly slower convection, but in terms of the total power much greater than in the Earth, is working in the Uranus and Neptunes. So in this neglection of the temperature-related heat stuff is always everywhere exceed, maybe except of Jupiter, it exceeds then the contribution from the P heat. And eventually we can remove this term from the thermodynamic equations. And so eventually we have the condition which is governed by the temperature variation, and it could be represented via the entropy, and here we could cancel out the contribution from the pressure. And so eventually we will consider the case when we consider the deviation from the adiabatic state, and here we have some hydrostatic state which we mark by C, and it could be found from the, okay, so, sorry, I didn't say correctly. There is the adiabatic state, and we consider only adiabatic state. There is the contribution to the convection, which is going down on the superadiabatic or subadiabatic value, which is very small in comparison to this initial value. And the same trick we are playing with the pressure, that there is adiabatic pressure and there is some small convective deviation which we are looking for, and it's going like this. And so then we, from the state of the matter condition and from some simple thermodynamic approximation, we can state how works this density, and it's work like that. And it's, of course, there is a stress for the contribution due to the entropy, and there is we can actually remove from the buoyancy term the contribution from the pressure. So eventually we have also the sum for the gravitational potential, and so eventually we, at the very end stuff, we introduce the effective pressure and how this system to solve, and it's subject to the standard boundary condition. And there is also temperature equation, and then we can further simplify this system for the terrestrial planets, actually using just one serious assumption. This only one serious assumption, but it's not allow us to lose the generality. And then we are now with the final system, which I already show you and comment very much. So then we make some estimation for the different variation, adiabatic variation of this stuff, and eventually we also add the boundary condition as we did in our previous estimations, and this boundary condition working like that. There is the adiabatic heat flux outside, and there is superadiabatic heat flux which go in another direction. So then this is boundary condition very similar to one I showed you in my previous lecture, but there is, here we just subtracted from this equation adiabatic value, and now this QO and QI have another meaning than we supplied on the lecture, on my previous lectures. And here we just have the deviation from the adiabatic state. So QO is not total flux, but the deviation. And also there is some integral conditions which work out in this case. And if we scale the units of all the stuff in the following manner, we take as the units of the length the radius of the outer core, then we use viscous unit for the unit of time, then we use this unit for the effective pressure, and then we use it for the entropy unit, and then finally we have continuity equation, equation of heat transfer, which is actually equation for the entropy, or more precisely the deviation of the entropy, and it also has its drive here, theta s, which is actually drive everything, and it could be obtained from the hydrostatic state. And of course there is Navier-Stokes equation, and there are two parameters here. One parameter is Ekman number, and another parameter is actually Rayleigh number R, and also there is of course Prandtl number. I just show it like here, because it's just from the definition we relate the viscosity and diffusivity. So we are looking for the condition that Ekman number is going much less than unity, actually up to the zero. And of course we specially investigated the case when the ratio of the inner radius to outer radius is roughly 1/3. And then we rearrange this boundary condition, which are with this scaling becomes like that, and like that the integral condition. And the main source term, which actually drive all the convection, can be represented via this stuff. This air dependence is due to the uniform heating of the floor with some heat which actually could be determined from the difference of these two heat flux. And also there is some part which is due to the differential heating. We heat one boundary at one boundary heat flux and another boundary at another boundary heat flux, and the general effect is R to the minus square. So eventually we are looking for the solution, as I already told to you. We are looking at the solution in that form, which has colloidal and toroidal component. And this is a big advantage of this representation, that if we consider the z component of the velocity, it's exactly equal this term, which is in fact the horizontal Laplacian of the this psi, which is actually colloidal contribution to the velocity field. And actually we can reduce almost all the problem to this value. And we are looking for the solution in this form. It's important to mention that we are still working in the sense of the globalization. Okay, in this global case, we have this value, but in the local approximation, it's just m to the some number. The k is just some number, but here it's not number, it's a function. And the main thing is that this function is roughly proportional to the square of s. So somebody thinks why we have here e to the 1/3 is the thickness of the layer in the phi direction, but e to the 1/6 it's in cylindrical direction. Initial analysis, which was local, state both value 1/3 for phi direction and the s direction. But here we introduce some general function here, general function under the integral, and it appears to be that actually this 1/6 is the consequences that this function Ks is in fact proportional, roughly speaking, to the sum delta S in square. So effectively, when we apply this delta S in square just to diminish, we are reduced from e to the 1/3 to the e to the 1/6. So this is, in simple words, this is the main reason of this approximation, while it's so perfectly local. And of course, we also have some expansion for the Rayleigh number, and it's interesting to note that this Rayleigh number is scaled like e to the minus 4 divided by 3. So it means that, for example, if Ekman number is 10 to minus 15, then this normalized Rayleigh number, which we normalize it by this Ekman number, it becomes of value 10 to 20. 10 to 20, so it's a huge value, by the way. Okay, so, and of course, it also can be expanded in this manner. And of course, we arrive exactly at the same equation as we have for the sphere. Because it's not dependent on this equation. Actually, we should understand that this equation depends only on z coordinate in terms of the derivatives. But the cylindrical value of s, this function of s, and this m squared, which is going for the azimuthal coordinate, everything. But it's necessary to stress that this dependence of the k function is entering like k square. One can think that the m function is also going like a m square, but no, it's not, because there is some m contribution here, which is actually going from the Coriolis force. So there is a contribution like m, and this is the reason why in the phi direction we have this e to the 1/3, and that the k is squared So in this direction, we have actually the dependence like e to the 1/6. And so eventually we operate in the similar fashion like we did in my previous lecture about the sphere, and we can expand all the eigenvalue. Here there is a representation of eigenvalue via the you see that this eigenvalue enter in this equation via the imaginary units I. So actually this eigenvalue, this part of the eigenvalue is the growth rate, and this part of the eigenvalue is responsible for oscillation, for harmonic oscillation. So, but anyhow, we reduce all this problem to the one a bit lengthy, of course, equation, but this equation is second order ordinary equation, and there are a lot of stuff here as well, but all this stuff is working like a parameter. So we can run for the different parameter to find the very various and very different current regime. And so there is some instability result, which we also calculated for all these cases and compared with a numerical calculation, and they are all listed here, and there is almost perfect coincide with the numerical calculation, and there is also some good agreement with the previous work. And briefly, maybe the most important cases for the turbulent instability with Planck number equal 1 is listed in this table. Of course, there are many other results, but we cannot calculate a lot numerically with any approximation. But nevertheless, we can consider this asymptotic solution. Okay. And perhaps, okay, maybe I was too. By the way, it's maybe one of the reasons why I shortened this stuff a little bit, because there is still one more theme which remains. So maybe I'll choose the way just to present the remaining 2 lectures in one, because we have no more time. So maybe there is some short question about this first part of the convection in the spherical shell, and there is also some link to the planetary magnetic field characteristic. So if you have some question, please raise. Yeah. Yeah. Yes. It was done with Maria for at least for some cases, which we consider as the most important cases, which could be represented the critical convection for the planets. We found the exact asymptotic solution and even compare them with numerical. Maybe you know that it's paper in GAFT 2006. In 2006, and I and Maria mainly were responsible for the asymptotic calculation, and Maslov, the third person, it is a numerical person. He calculated in full numerical. So and then we of course compare our result, and comparison was just perfect.
Oh. So spherical area, again it reduced to any 2-dimensional or something, or in 3D you have dealt with that.
Eventually we have one-dimensional equation. One-dimensional. Eventually this equation, which we finally have and which we solve, is this one. Okay. And it depends only on that. Of course, there are another variable which linked to the azimuthal coordinate, some particular m. There is some sources of the convective instability, which is also related to that. And also there is a lot of things. Eigenvalue, there is this m value, azimuthal value, and also there is some form of this function. But all of them can be regarded like as a parameter. But the dependence is only on that. And this is second order equation, and putting the corresponding boundary condition under the different parameters, we are looking for the most critical regime. And then when we have defined this critical regime, we can explore a very wide volume of the different regime, because we have asymptotic solution, so just in one this solution we almost have everything. So, and then it's worked perfectly.
Yeah, interesting solution.
Okay, so maybe I will finish up with our work was, at least I'll try to do that. Okay. It's F5 or how to make full screen?
Excuse me.
I forget how to make the full screen in PDF. Okay. I forget how to make full screen. Oh, this one. Okay, thank you. Sorry, I forget. And also, maybe I will like to finish up this presentation. Oh, it's in here, but there is no here. It's here on the book, but here there is nothing. A description of the unsettled strongly localized thermal convection in a rotating and spherical shell, which was done by Andrew Soward, Andrew Bassam, and myself. And there is some sort of the joke, maybe you know, what is the optimal number of the participant to write the good paper? Do you know the answer? It's 3. The optimal number to write the participant, the suitable and very good paper is 3. Why 3? Do you know why? The reason is quite simple. The first know what is necessary to do. The second know how to do. And the third, just what? Doing, just doing. Okay, so in this case, the idea was mine. And Andre Soward know how to do that, because idea was started by mine, but I, in a large extent, I didn't understand how to do that. And Andre Soward was clever enough to provide us with instruction how to do that. And the Andrew Bassam is a numerical person. He made the major numerical calculation, and you also should take into account that actually the numerical calculation here are two sides. There is some numerical calculation for the full numerical problem, in which we don't make any assumption about asymptotic or whatever. So this is direct numerical calculation. But also there is numerical calculation to handle with this system, with this reduced system. Of course, it's just second order system, relatively simple, but we should investigate in the vast volume of the different parameters, in the tremendously vast. just to get all the possible solution. It's also will hard numerical work, because you should see all the possible angel value, compare them between each other to find the most critical, the most suitable one at the maximum or at minimum or whatever. So it's also complicated numerical work. And actually, Andrew Bassam was the person who made a lot of this work, because perhaps he was the main worker in this problem. Okay, so let's start from the introduction. Introduction is that the onset of instability of Boussinesq fluid with rapidly rotating shell is considered. When a thin unstable layer lies adjacent to the inner sphere boundary radius, which is denoted like that. This layer, which is of radial extent, is proportionally to the epsilon square, sits beneath the remaining stability stratified fluid. The variable stratification is affected by a combination of differential heating between the inner and outer boundaries and a uniform distribution of the heat sinks within the fluid. And this, at this point, I should mention that eventually this system with a strong concentrated instability could be responsible for the magnetic field of Mercury, because this is quite unusual magnetic field, and it's perhaps because of there is two sort of the mixture between the stability and instability, and actually at some very thin place there is the instability, and another place there is a stability. So this is the playing game, and so there is actually very strongly concentrated instability, and it's work. And as in the previous small Ekman number studies, okay, all these previous Ekman number studies I speak loud about too much, convection takes on the familiar cartridge belt structure, which in view of the differential heating is localized within the thin layer adjacent but outside the tangent cylinder to the inner sphere. It was first done by Domi. We consider the situation when the domain of convection sits entirely within the unstable layer, which requires that this epsilon is, which actually restricts the condition of the strong concentration, should sufficiently exceed e to the 1/8 hour. So, and this condition is satisfied for our case. And in this case, the axial extent of the convecting columns from the equatorial plane is small and of size or of this size. And then let's make the formulation of the problem. Of course, the formulation of the problem is quite similar as we already did with you, but maybe in the more classical way. Here we Ekman number, you know how, and also we have the the Rayleigh number, also very well known. Here the T prime is temperature gradient, which is negative, so we have put, to have this value positive, we put minus here. There is a Prandtl number, and there is a ratio of the radius, and eventually we arrive exactly at the same, almost exactly the same equation as we already explored with you. Here there is a Navier-Stokes equation, and there is an entropy equation actually, which work here from this drive. And also there is a drive which is actually depend, and also the coefficient is satisfied for the thickness of this strong instability place, which is outlined like that and like that. And it's there is a condition on it which rather wide condition, and it's allow you to investigate the different cases of this instability. And at the limit of Ekman much less 1, actually we are working out the quasi-geostrophic approximation appear. Related to cylindrical polar coordinates, the most unstable models from a cartridge belt touching but exterior to the tangent cylinder S equal 1 to the inner sphere with a structure proportional to. So actually all this cartridge belt structure appears near the inner core. here I didn't wrote the inequal, but let's wrote it here. And actually in this things we have like this. But eventually, if we consider the case, it's for the case of the Earth, but more precisely this situation is for the Mars, and there perhaps, not Mars, Mercury, where this unusual magnetic field, and it's maybe much larger. And in this case, our stuff sits somewhere here. So this is the inner core, this is the outer core. And it's like situation which is in Mercury. Okay. So, of course, we explore exactly the same things as we did with you. So the main property and everything is almost in parallel as we done. There are, of course, some difference, but not so much. Actually, it's the same. And then we suppose that there is strong stratification which scale it like this epsilon. And this strong stratification should satisfy this approximation now in two parameters. There is Ekman number and there is this epsilon parameter, which we first suppose that it's small. And in this case, we can obtain all the system in rather simple form. Again, we have this second order. There is two first order ordinary equation. And so effectively it's the second order ordinary equation to which, and they are relatively simple. And also there is such a relation which is satisfied. And actually we also, this all analytic solution we obtained, and we have compared with the numerical solution. And this numerical solution was done for the case of the this W KBG. We solve the tangent cylinder equation numerically subject to the symmetry, which is actually symmetry manifested like that. And also we suppose non-penetration condition on the outer boundary at this value. And also we suppose that there is actually this non-penetrative condition to reduce in our notation to this azimuthal component and latitudinal, not latitudinal, azimuthal component and component in the direction of the axis rotation. And also this aspect ratio also which says that how strong is this layer can be represented like that. And of course we first of all choose for the Earth condition and plot stability boundary representation at different Ekman number just to cover as much as possible situation. And then eventually we investigated for the Prandtl number equal 5 numerically. And we investigated the different cases, especially for the azimuthal wave component and separately for the Rayleigh number and for corresponding time dependence part of this value at the critical parameter. You know that at the critical position, the eigenvalue which is responsible for the temperature dependence has 0 growth rate, but there is frequency. And this is exactly the value we are calculating, independence of the, and also we have could calculate the corresponding Rayleigh number, and it's become critical somewhere here, here, and here at the different position. And for each critical case, we have different variation of the frequency. Effectively, this is the frequency in these terms. And it's, you see that first there is some stabilization, then frequency is declining, so period, characteristic period is rising. And also there is calculation, similar calculation for the Prandtl number equal 1, which is perhaps more interesting for the case when we have this situation. And a situation with turbulent transport. And then there is also calculation for the p equals prime number equals 0.8. Of course, there are some difference between this pictures, but qualitatively are almost the same. And there is next prime number we explore, and next one, and the very next one prime number, perhaps the most close to the Earth condition. Oh, sorry, this one, most close to the Earth condition, this one. And it should be noted that this situation also can work in the Earth, especially in the case if here there is at this outer position, there is stabilizing layer somehow. So in this case, there is stabilizing layer in this concentration in order of epsilon. We should come here somewhere. And so in this case, this condition could work if we indeed have a stabilizing layer near the outer boundary. And so let's draw the conclusion. Oh, no, sorry, not conclusion. Okay, just we consider it the numerical result. Of course, we should compare this numerical result with asymptotic expansion. And here the various things which we get from the asymptotic expansion are listed here. And and then also there is two modes of the received solution. One mode is slow mode, which is actually zero frequency, and almost no time dependence at critical level. We didn't instigate to a critical level. And there is a fast mode where this frequency is not zero. And there are two fast modes which we denote by the plus and minus sign. And the property of this fast mode is that this zero order Rayleigh number normalized by the epsilon in for third power is working like that. And they are only exist under condition of the Prandtl number less than 1, which is perhaps quite suitable for the Earth. And they bifurcating imperfectly from the slow modes in the vicinity of this azimuthal value of the azimuthal number and allocated in this region. And also we can consider zero order solution of this problem, and this is actually reduced the lowest order terms which could be determined in this way, and with together all this together yields the following relation, and the real and the imaginary part provide four equations for four unknown actually. So this is actually now we even simplify further this system to the algebraic equations. And eventually we can consider the case of small Ekman number. Some marginal solution could be found for the different value of Prandtl number. And all of them, most of them are listed here. Again, for the same dependence, we have azimuthal wave number. Here we have a frequency. And here we have the correspondent scaled Rayleigh number. And of course, there are different cases we investigated, and this is actually asymptotic cases, and part of them we compared with the numerical solution, which I showed you below. And then there is another cases. So we, of course, investigated plenty of cases. And there is a first order approximation in this system also. The things I just showed you before is the first order approximation, but we managed to proceed even to the second order approximation to find with more accuracy. And again, we have the similar result as we got in the first approximation, but there is a slight difference. And eventually we again investigate different cases. And this is, there are some amount of them. And also there is pitchfork here, and it's working like that. I will not stop on the detail. Let me show another picture where actually Andrew Barson produced all this wonderful picture. It's a numerical picture with very different parameters and very different scaling for this epsilon. And also we, of course, calculate the critical values, which are can be expressed in the zero, or maybe more precisely to say first approximation, because it's quite valuable. And we found we represented via the root of order 3 from the Prandtl number, and this is the effective Rayleigh number divided by corresponding power of Ekman number. And we estimate all the stuff. And eventually we just formulate the summary. The agent solution of the odd governing the axial structure have been obtained both numerically for moderate but small values of the stratification parameter epsilon, and analytically for the small parameter much less than 1. The condition of this solution is that analytically we can investigate only this case, when there is a strong concentration of the parameter. But numerically, of course, we can investigate everything, and partly we investigate this case to confirm analytical solution, and also partly we investigate the case when this epsilon is of order 1, and even less, and even it could be actually even negative. And at the zero order, the solution resembles that for classical plane layer convection. Actually, it's interesting that in the zero order, it's quite similar to the plane layer convection, exhibiting exchange of stability and overstability, as it was in the very well-known work of the Chandrasekhar in 1961. But only this work for the Prandtl less than 1. The set of the convention for Prandtl much larger than 1 is steady, but it is oscillatory with the frequency of what is this omega star, which we also estimate for Prandtl number much less than 1. So there is sort of the opposite things, which is possible again to do approximately for larger Prandtl number and for smaller Prandtl number. We managed also succeed to estimate some part for the first order approximation, so in fact it's a second order approximation. And this curvature removes plane layer degeneracy. Actually, as we already told, there is like the plane layer, Chandrasekhar plane layer, but if we go on to the further approximation, you see that it becomes not like this plane layer. There is some feature that is responsible for this particular model. And also it's important to mention that there is slow modus, and in these models a low frequency oscillation has of the modes caused their short axial columns to propagate slowly, actually. And also there are fast modes. The magnitude of both the Rayleigh number and frequency of the two this mode split, and when Prandtl number is less than 1, the slow models for m much larger than 1 make a continuous transition to the preferred fast models for m equal much less than 1. And also there are critical modes, because these critical modes perhaps the most interesting for us, because they are related to the critical condition in the planetary convection, and at all values of p, the critical Rayleigh number correspond to a mode exhibiting rate propagation, whether it be a fast or slow mode. This feature is shared by the uniform classical convective shell models as well as Bousset annuals model. So actually this feature is inherited from the classical view. And those modes do not possess any stable stratification and typically are prone to easily executable Rossby or inertial modes of convection at small Prandtl number. By way of construct these structures cannot exist in our model for small epsilon. I remind you that this is stratification parameter. Due to the viscous damping in the outer Zig stable region, and our critical Rayleigh number is larger by the factor of P2 minus 1, of course, on the condition when this Prandtl number is small, then those models actually will predict. Okay, so seems I finished. Maybe the most important things are all listed here. So, and in terms of application, I again told to you that perhaps the most best approximation of this model is for the mercury magnetic field in such a picture, in such a cartridge bell cylinder. And also it's possible for the Earth, but only on the condition that there is a stably stratified layer which is against convection, and there is some position where this convection instability is concentrated somewhere here. Maybe I'll mark it like that. Okay. So it seems I finished everything. And maybe in a time. So is there any questions? Yeah, please. Pitchfork bifurcation.
Yeah, you spoke about imperfect pitchfork bifurcation in one of your slides.
It's okay.
Yeah, this one. So, are there any other such bifurcations like Hop bifurcation or transcritical bifurcations that can be determined?
Actually, in our system we found only this type of the bifurcation actually, but we are not sure because maybe we didn't explore some parameter where there is another bifurcation. But at least in domain of the parameter which we investigated, it was only such a bifurcation.
And what is the bifurcation parameter here? Is it the Rayleigh number?
Okay, let me see. Yeah, exactly. It's Rayleigh number. Yeah, you're right.
Thank you.
Okay. Okay, look, there are more questions. It's semi-finished in the time.
Yeah. Okay. So, thank you, Professor, for your enlightenment talk about the last one. Summary is very good. You summarized everything.
At least I tried to catch everything, even though that was somehow delayed. Now I succeed to complete the picture.
Complete. Yeah. Okay. Let us thank Professor Sergey. Yeah.
Thank you to you for your listening. It's more important than speaking.
Yes.
Everybody can speak, but not everybody can listen.
Yeah. So, thank you so much. Again, we will meet here by 2 p.m. for the valedictory function. Okay. So, as usually, you can go to Kalam Hall and finish the lunch. Come here by 1:30, if possible. Okay. Okay. Thank you.
Okay. Thank you.
valedictory function of 10 days Gian course on hydrodynamics and critical convection in liquid course of terrestrial planets, organized by Department of Mathematics, NIT Warangal. This occasion marks the end of February 2025 that has been filled with both challenges and triumphs, where we have grown, learned, and created lasting memories. We extend our deepest gratitude to our respected mentors and organizers who have guided us through this journey. Without their support and encouragement, none of this would have been possible. Today's function will be a celebration of our achievements, and we will hear from our inspiring speakers, reflect on our time together, and bid farewell to this chapter with fond memories. Now I request our special guest of honor, Professor Sergei V. Starchenko, Chief Scientist and Head, Main Magnetic Field of the Earth Lab, Russian Academy of Sciences, Russia, to kindly come over the stage. And the event is graced by Professor R.S. Selvaraj Sir, Head, Department of Mathematics, and Professor S. Srinivasa Rao, Dean, International Relations and Alumni Affairs, and Professor H.P. Rani, Course Coordinate, Department of Mathematics, kindly come over the stage. Ladies and gentlemen, let us all stand in silence and respect to reflect on the strength and beauty of our nation as we hear our national song.
श्यामला मातरं वन्दे मातरं शुभ्रज्योत्स्ना पुलकितयामिनी पुल्लकुसुमित द्रुमदलशोभिनी सुहासिनी सुमधुरभाषिणी सुखदां वरदां मातरं वन्दे मातरं वन्दे मातरम्.
Thank you for your heartfelt respect and participation. Please be seated. Without further ado, let us begin our ceremony. Now I would like to invite Professor H.P. Rani to deliver the valedictory address.
Good afternoon to all of you. I welcome our beloved Dean, International Relations and Alumni Affairs, Professor Srinivas Rao sir, and also our HOD of the Department of Mathematics, Professor R.S. Selvaraj sir, and today's chief guest, Professor Sergei. And our beloved dear faculty members, scholars, participants, and also the scholars from other departments also. I welcome all of you for this occasion of valedictory function of this 10 days journey. This journey not only started today, it has started in 2020 itself. We have applied for this program in 2020 and it got sanctioned in the last year, and due to some restrictions going on, Professor Sergei decided to come here during this time. Okay. So we have a long history of this one, the behind the scenes. As you are aware, today is the National Science Day, and Nobel laureate Subramaniam Chandrasekhar's uncle is Sir C.V. Raman. So on this occasion, celebrating this valedictory function of this hydrodynamic stability, mainly we have discussed in this course, I am privileged to be here. So the Indian-born astrophysicist Nobel laureate Subramaniam Chandrasekhar presented his work, especially in the black holes. So in this connection, we keep on working about this one, for many eminent scientists are in this field. So we have chosen our topic as hydrodynamics and critical convection in liquid cores of terrestrial planets. This course started with the Professor Sergei's lecture from the basics of planetary hydrodynamics and rotating coordinate system. It helped us easily to understand, including our postgraduate students also, to follow his lectures. Then he gradually moved on to the initial equations for geostrophic flow with characteristic quantities. Mainly, he has given a detailed analysis about the asymptotic expansion and Ekman layers in a spherical shell. Especially, he used to give many tasks to solve during the courses and after the courses also. Then we have invited the external expert, Professor Rameshwar from Usmania University, to speak about weakly nonlinear analysis. Especially he talked about hydrodynamics convection using regular and singular perturbation methods. He also solved many problems related to this topic. Then our Spark expert who is here, Professor Maria from Russia, discussed about the different problem solving techniques in linear stability analysis and how to find the critical Rayleigh numbers using analytical methods. I also participated in these lectures by giving diffusion convection equations for steady and unsteady problems using the computational method finite volume methods, and solved these problems using MATLAB in our mathematics lab itself with the help of our department. Thanks for providing the department lab, even though the classes are going in the full swing now. And also at the last, yesterday we have solved some classical plane layer problems using finite difference and spectral methods. So there were around 30 lectures and 10 tutorials. Outside the classes also, participants have very detailed and depth which contains 2 credits for this Gian course as prescribed by Ministry of Education. And also our administration of NIT Warangal has accepted to consider these credits for the PhD scholars and also for the students. So all participants have prepared the presentations with the dedication. Everyone has chosen one topic which are given in this course. To keep the participants active in these 2 weeks, we have arranged yoga and meditation sessions to refresh their minds throughout the course. Thanks to our wellness club, especially Professor Amba Prasad, Professor Gaurav Kumar Sharma and the trainers from Warangal. Not only this one, we have arranged after the class hours, after 3:30 or 4:30, to visit the places like Ramappa Temple, which is recognized by UNESCO, Warangal Fort, and we have requested the Telangana Tourism authorities to play the laser show, and Ramalingara Swami Temple in Mettugutta. We have climbed up the hill and enjoyed the sunset especially. Sunset also there and light show also going on. So before the Shivaratri, we have got a chance to go there and pray the God very peacefully without any crowd. These are all marks of the Kakatiya dynasty who has ruled Warangal for more than 300 years. We can able to acknowledge the dedication of Ganapati Deva, the king who ruled Warangal, and Rudrama Devi's bravery, which are there still in our blood and hearts also after seeing that laser show. Dear participants, I hope you have enjoyed this fruitful academic journey through Professor Sarge, Professor Maria and Professor Rameshwar, our administration, faculty, scholars and students. Please take the good memories, and if you have faced any problems during our stay here, please bring to our notice. This will help us to improve ourselves further in the coming days. Thank you.
Thank you, ma'am. Now I would like to invite Professor R.S. Selvaraj sir to address this gathering.
Today's chief guest, Professor G. Strachenko, who is also the star of this Gian program in the last 10 days, and respected Dean, Professor S. Srinivasa Rao sir, Dean of International Relations and Alumni Affairs, and the organizer of the program, Professor H.P. Rani, and all my faculty colleagues and participants and scholars and the students of this institute. And a very good afternoon to all of you. And it is indeed a rich academic experience you have undergone last 10 days. I am very happy to note that this is the 7th Gian program of the department, and previously 6 Gian program was successfully held, and this is the 7th program. And I also have to congratulate Professor H.P. Rani, who has been spearheading. I think she has completed nearly 5 Gian programs. This is the 6th one for her in the department. So department takes proud in saying that Professor H.P. Rani has done a great thing for the department, bringing the department into the limelight of Gian programs. And there is one more program also is yet to come in the next week, Spark program, jointly with the Mechanical Engineering Department. Professor Jay Krishna sir is here, and who is also part of our collaboration. It's very nice to see that department collaborates with another department. It's a very happy note I'm saying this. And we are also expecting another program, Teachers Enrichment Workshop, through MTTS in the month of April. So we are going to be filled with some academically enriching activities in the coming days. Okay, and at this point of time, I also like to congratulate all the participants who are here and who have not only undergone an academic wellness program, and also mental wellness program as well as physical wellness program we have undergone, it seems, in the last 10 days. It's really nice that participants have got enriched with this 10 days workshop academically as well as physically as well as mentally. And this academic enrichment which you received from this workshop, we anticipate as a department, as an institute, we anticipate that you carry forward this to your institute where you are doing research. Not only with, whatever knowledge you have gained here should be useful in your research. That is what the purpose. And so that you will have collaboration with our department also. There are nearly 11 faculty members who are working in a similar area which you have been gone through the last 10 days. So all the faculty members should be helpful in collaborating with you. That is there. Okay. So whatever doubts, whatever clarifications, whatever discussions you want to have in future, our department is open to that. Okay. So you can contact not only Professor Rani but also all the faculty members of this institute, who will be very much helpful in clarifying your doubts or collaborating with you or doing any kind of activities in future. Okay. So we look forward your participation, your involvement in any further activities of the department. Okay. I wish you all the best. Thank you.
Thank you, sir. Now I'd like to invite Professor Srinivasa Rao, Dean, International Relations and Alumni Affairs, to address the audience.
Respected Professor Sergey Starchenko, and Head of the Department of Mathematics, Professor R.S. Selvaraj, and Coordinator of this 10-day Gian course, Professor H.P. Rani, and another professor from Russia, Professor Maria, and other faculty members of the institute, dear participants and research scholars, and all the faculty members of the Department of Mathematics and Institute, and research scholars of the Institute, as well as participants who have actively involved in attending the classes. So my special thanks to all of you for listening to the professor for past 10 days. So along with you, Professor Maria also might have become one of the participants for listening to the lectures. So my thanks to her. So this course came to an end. We know that this is the Gian course, 10-day Gian course. This you might have got a lot of knowledge on this hydrodynamics and critical convection and liquid crores of terrestrial planets. So 10-day course is not a small thing. Daily 4 to 5 hours lecture as well as interaction with the professor, you might have got a lot of knowledge. So definitely this Government of India objective is getting fulfilled by inviting foreign faculty to the Indian institutions and making interaction with research scholars, participants, and Indian institutions, as well as making further and further collaborations. My special thanks to the organizing team at IIT Kharagpur for coordinating all these Spark activities, and we all know that NIT Warangal have its own name in the country, and it is having a lot of significance, and it has identified and it has proved itself at national level with this Government of India schemes, as well as the faculty who are making collaborations with various universities under the dynamic leadership of our director, Professor Vidyadhar Subudhi. Definitely within a short duration, our NIT Warangal will get a lot of international significance and recognition also. So my thanks to Professor Sir for staying at NIT Warangal campus and visiting the historical places around Warangal, and you might have acquired sufficient knowledge about Warangal city also, along with sharing knowledge, your knowledge to the participants. So wish you all the best to all of you. All of you may be going with a lot of knowledge, experience, and exposure about this topic. Definitely it will be useful for you to do better research works, as well as guiding undergraduates and postgraduate students project works. Wish you all the best to all of you.
Thank you, sir. Now it is the moment we have all been eagerly waiting for. We are honored to have with us today a distinguished guest who has not only contributed immensely to the magnetism and aerodynamics in the Earth, other planets, stars, and other galaxies, but he is also an inspiration to all of us here. So without further delay, I would like to request our esteemed chief guest, Professor Sergey Stachenko, to please come forward and address the gathering.
Hello to everybody. I'm addressing to the estimate institute coordinator, estimate head of this department, estimate the actually the person who ran all this project, and but especially I am grateful and want to say a lot of greeting to the special estimate students, because students should be put in the main corner, and because everything is done because for them, because they are not our future, and then that they create this real science. Of course, with some help of us, we trying to achieve the best result. And in this respect, perhaps your place is maybe one of the most prestigious place in the sense, because actually we won very difficult competition to get this Gian grant. And here I show my deep respect to the estimate Professor Rani, of course, first of all, because only due to her efforts everything comes in motion, and actually we eventually have second Gian course led by me. She managed to do that even too. And on top of that, now we have another Spark course, which is actually the most prestigious. This course is for 2 years duration, and as a result of this course we are now writing the monograph. And this monograph should be a quite useful book, again, for the students. Everything for students. I'm just a slave of the student. And I hope that also you do everything to promote the science. And it's interesting to say that the promotion of science in India is quite clear now, because they are spending their effort to invite such foreigners who is a true expert in some field to you, and it's I see really how it's helped to students to understand sometimes very difficult things. Sometimes they even understand something that I not understand. So actually you have quite high level of the student, and with your scheme of the support from the abroad, from the different value person who will be involved, and this development could be proceed even further, and I hope that it will do. And especially, of course, I have a hope, and not only I, but all the students with whom we're working, and of course, Professor Rani, we have a hope to develop further this collaboration, and this collaboration is very fruitful, and I see that it's maybe we will rise even more fruits on this tree, and eventually we become maybe valuable scientific contribution will have, which will raise the Indian scientific ability, and especially again I am speaking about students, and you have the form which in part was organized by Professor Maria and especially by Professor Rani. They invented some new approaches to test the students, to support them in the way to better understanding of all this very difficult and some part science. So I am very grateful to them and hope on the further collaboration. And actually now Russia is open for the some big collaboration, including some postdoc and other things, PhD position where you can finish your PhD in Russia, I think. So actually, all the way is open, and it could be quite nice if you and your leaders will guide us to the prosperity future where we will be quite successful. Let me finish my speech with some maybe not official, but some quality things. I just want to confess that everybody everywhere in the world, and actually, especially in Russia, the people regard that the Russian girl as the most beautiful, and they think that it is the rule. But here in India, I start to understand that there is another country where there are quite beautiful ladies, and maybe they can win in this competition. Okay, let me finish on that.
Thank you, sir. Ladies and gentlemen, it is now time to express our heartfelt gratitude to our guest, Professor Maria S. Kotelnikova, Faculty of Department of Mathematics, Novosibirsk State University, Russia, for this gracious presence today. Now, I would like to invite Professor Srinivasa Rao to felicitate our guest, Professor Maria S. Kotelnikova, with a shawl and memento. Now I request Professor Srinivasa Rao to felicitate our guest, Professor Sergei V. Stachenko and Professor Maria S. Kotelnikova with the Institute souvenir. We acknowledge the contributions of all the mentors, organizers, participants, and students who made this journey a success. Your commitment has truly been remarkable. We now come to one of the most awaited moments of today's valedictory function, the distribution of certificates, which recognizes the hard work, dedication, and accomplishment of each participant. Now I request the participants to come forward to receive their certificate for outstanding performance during the course. Now I request Subham Satyam to come forward and receive his certificate. Mritika Das, I will call one by one. Okay. Fine. I like that. Okay. Now I request Professor Srinivasa Rao sir to give the certificates to the participants. Subham Satyam, Mritika Das, Anup Suresh, Mritika Das, Anup Suresh, Shubham Kumar, Kamlesh H, Let's we encourage our participants for their hard work and their keep on efforts. We have to encourage them, no? Kamlesh, Akansha, Rajesh Chari, Dubashi Bharat, Mogilaju Naveen, Manisha Jangir, Sendil Kumar T, Now I request Professor Sergey V. Starchenko to give the certificates to the participants. Swati, Abhishek Gupta, let's applaud for them. Abhishek Gupta, Preeti, instead of Anusha, Dubashi Bharat will take her certificate. And instead of Ankita, Anup Suresh will take her certificate. Atul Kaushik, P. Pradeep, Okay, you just take it. Okay. Harika, Kankana. Thank you for your dedication and enthusiasm. We wish you all continued success in your future endeavors. It is with great pride that we now move on to the distribution of grade sheets. These certificates recognize the hard work and excellence of our participants. As I call your name, please come forward to receive your grade sheet, which symbolizes your commitment and efforts toward the course. So please join me in congratulating our participants. First, I request Anup Suresh to come forward to receive your grade sheet from Professor Saigivi Stachenko. Grade sheet. Kamlesh H. Kankana. Preeti. Mogilachu Naveen. Dr. Sendil Kumati. P. Pradeep. Let's applaud for them for their efforts and dedication. It has been honored to witness your growth and dedication. May this great sheet inspire you to continue striving for excellence in everything you do. So thank you to all the participants for your excellent contributions. We look forward to seeing all the great things you will continue to accomplish. On behalf of the entire organizing team, I extend my heartfelt congratulations to each one of you. Your efforts have made this event truly special. Before we conclude today's event, we would love to hear your feedback. Your feedback is incredibly valuable to us, as it helps us to improve and make future events even better.
Okay, a very warm good afternoon to our respected guests present on the dais and to all the participants, to all the research scholars of this institute, and to one and all present here. Myself, Kankana Deori. I am from National Institute of Technology, Arunachal Pradesh. My hometown is Assam, Guwahati. So as a participant, when I first registered for the course, I basically had only a few idea about this, but I intended to, with my supervisor's guidance, I applied for this course. And when I came here, frankly speaking, for the first 2 days, I couldn't understand properly because all the things were new to me. But as time grew and days passed, I came to know the essence or the real meaning behind learning a course. We have to know the basics of it. And thanks to Professor Sergi sir and Maria ma'am, they guided us very well throughout the course, along with our coordinator ma'am, HP Rani ma'am, who taught us some very basic and integral part of mathematics methods, which I will be able to apply in my research work. So from here, I'm not only taking a few things or materialistic things, but I'm taking a lot of experience, which I'll be very gladly happy to do my independent work or collaborative work. And also apart from that, the 10 days course is not a short duration. So ma'am, our coordinator ma'am, made sure that we don't get stressed at all. So she inspired us to join yoga and meditation sessions. She made beautiful trips to Warangal, some historic places, because this is my first time visiting here. As Hyderabad in NIT Warangal and as a whole Warangal. So I got to experience a lot of new things, and also most importantly, I came across many wonderful people here. As some participants, we were able to, when we first introduced ourselves, we were all from different states and different area or domain of work. But as the course started, we engaged ourselves in some fruitful discussions and workings, like doing our tasks or assignments together, sitting in the exam and learning the most out of it. And also the research scholars from here, they helped us in like looking towards small needs, like from accommodation to our food, and also accompanied us in our short trips. So I'm very thankful to them, and I hope in the future also we'll have this connection, we'll keep this connection. And also thanks to all the professors and all the NIT institutes, esteemed professors, deans, and director sir, who is unfortunately not present here. But as a whole, I would like to thank all the members of NIT Warangal for having us here and giving us this wonderful experience to take on forever. Thank you so much. Thank you.
Good afternoon, everyone. My name is Anup Suresh, and I'm from Bangalore. I'm a research scholar in VIT, Vellore Institute of Technology. So when I first came here for the 10-day Gian program, I didn't exactly know what to expect, because this field was something this field of geophysical fluid dynamics was new even to me. And I took this course not because of my guide or because my guide forcibly asked me to, because I was genuinely interested to study such a course. And my curiosity was thoroughly satisfied by all of Professor Sergi's lectures, as he delivered them beautifully. He made it look, he made such difficult concepts look very easy and explained it in a very simple manner. So I would just like to thank Professor Sergi and Professor Maria and Professor Rani and all the course instructors who made it look very easy, made the subject look very easy. And and thank you for the, I would also like to thank NIT Warangal for the amazing hospitality it provided us for the last 10 days. And also to my fellow participants, which made my learning experience very beautiful. So thank you. Thank you.
Yes. Thank you. Thank you for taking the time to provide your valuable feedback. We truly appreciate your input and will use it to continue improving. Ladies and gentlemen, for the wonderful time we have all spent here together over past 10 days, which has been so enriching and enjoyable. It is our duty to express our gratitude to all those who have contributed to making this occasion a grand success. It is my honor to invite Professor Y. Srinivasa Rao to deliver the vote of thanks.
Okay, thank you, Archana. A very good afternoon to everyone. It is my great privilege to propose vote of thanks on this auspicious occasion of the valedictory function of the 10-day Gian course on hydrodynamics and critical convection in liquid course of terrestrial planets, organized by Department of Mathematics, NIT Warangal. First and foremost, I extend my heartfelt gratitude to Professor Vidyadhar Subudhi, Director NIT Warangal, for gracing this occasion with his presence, with his absence, due to various reasons, and for his unwavering support in organizing this course. A special and profound thank you to our esteemed chief guest, Professor Sergei V. Starchenko, Chief Scientist and Head, Main Magnetic Field of the Earth Lab, Russian Academy of Sciences, Russia, for his invaluable time and for sharing his knowledge with us. A sincere thanks to National Co-Coordinator, GAN Courses, IIT Hyderabad, to make this program possible. I sincerely thank Professor S. Srinivasa Rao, Dean, International Relations and Alumni Affairs, and Institute Co-Coordinator for GAN and Spark programs, for his continuous guidance and support in making this event a reality. My deep appreciation goes to Professor Shirish, Dean Research and Development, for his encouragement and constant support in facilitating this program. A heartfelt thanks to Professor R.S. Selvaras, Head of the Department of Mathematics, for his unwavering support in organizing this GAN course. I also extend my gratitude to Professor Abdul Azim, Chief Warden, Professor J. Pranita, Deputy Chief Warden, NIT Hostels, for providing accommodation for the participants. A profound thanks to Professor Shankar, in charge of Kalam Guest House, for providing local hospitality to the chief guest. A special mention to Professor H.P. Rani, coordinator of the program, for her dedicated efforts in ensuring the smooth execution of this event. I also extend my sincere thanks to all deans, heads of various departments, faculty members, research scholars, supporting staff, present media, and webmaster for their valuable contributions to this event. Lastly, I would like to express my immense gratitude to all the participants for taking this initiative to attend this program. Thank you all once again. Thank you.
Thank you, sir. At this moment, I would like to draw your attention and request everyone to stand up for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उज्जल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you all for your participation and attention today. We are now delighted to invite you to join for a high tea which will be served outside of this hall. Thank you to everyone. Thank you once again.